Thank you so much for joining us today. I am Jessica Rodriguez, and I am the Industry Engagement Officer for the Data Science Institute here at Columbia University. Today's seminar is an iCubed, which stands for Institute, Industry, and Innovation. These seminars connect our industry affiliates to our students and the larger Columbia community to explore topics at the forefront of industry. We invite data scientists, engineers, or researchers from our affiliates to give a talk about a recent project or case study. During these educational events, we encourage attendees to ask questions via the chat and Q&A feature. At the very end, we'll have a Q&A session and you'll be able to exchange ideas with our guest today. Today, we have a data scientist from Capital One speaking. Today's talk will be Dynamic Customer Representation, Learning in Finance. This will be presented by Sam Sharpe, who is Machine Learning Research Scientist at C4ML Applied Research at Capital One. Welcome, Sam, and thank you so much for joining us today.
Thank you. Great to be here. Yeah, so I can get started. Let me see here. You see my screen now? I just switch this up.
We can see it.
So, yeah, I work on our applied research team. And we basically try to bring a lot of outside research into Capital One to see where we can apply it to different applications around Capital One and different lines of business. So this is work with some of our digital data scientists working on digital data from customers in our online web apps and applications, and trying to use that to inform some of our downstream models in our company. So this is, we also published a paper based on this kind of research, which I can also share the link at the end as well. So we have a lot of different data streams when it comes to customers for Capital One. We have anywhere from emails that get sent out, messaging in our apps, chatbots, different mobile web clickstream data. And so all of these different complex data streams are pretty heterogeneous. And we want to be able to kind of combine all these sets of data into an easy way to use this capability to make it readily available for other decision-making systems around the company and places where we can basically deploy our models for different types of problems that we want to solve around the company. And when we think about like how our data streams can be combined, there's a lot of interconnectedness between what customers do in these different areas around the company. So, just as an example, looking kind of at transaction data streams and online web activity data streams, we can get a lot of information by looking at some of by basically connecting some of these events together. So for example, in terms of, maybe someone comes onto our web app and they have a lot of repeated sessions trying to do the same thing online. And then that might be indicative of someone trying to call in to the call center because they have a problem in the future. People might also come in to check their balance, and that might be some pattern that we were able to see by looking at how money is flowing in and out of accounts versus when they're coming to log into the app to check their balances. And it could also help in terms of trying to detect fraud, where maybe there's some change of address or a change of a password, and then there's some odd large transaction in another state. So some of these different data streams can help us kind of foresee some of these things that are going to happen, and therefore kind of help us to use these predictions for things like fraud and customer servicing. So Our digital clickstream data at Capital One consists of more than this, but this is basically kind of what we use for our application. So what's contained in here is a collection of events. So when you log in, when you view a certain page, when you click on a certain button, all of these different actions are recorded along with information about the mobile device, the geolocation, and different names of the elements and the events. And so these are kind of what we call collected into a session. So these sessions can sometimes be hard to pick up because people maybe time out of their session and log back in, but mostly it's just indicated by a login and a log out. So you'll log in, do some, go to the home page, do a transaction, pay a bill, and look at your statement. And all of these can be tokenized into these different actions. And one of the problems with this is that it's a lot of data, as you can probably guess, and it's very highly dimensional. So we have tons of different actions that can happen, tons of different buttons that you can interact with, things that you can view. So modeling this becomes pretty complex. So this is where we kind of look to representations and embeddings. So if you're not familiar with what representations and embeddings are, they're basically taking our highly dimensional data and trying to map it to a lower dimensional space where we can still preserve some of the relationships between our data, but also be able to more easily build models with it, deal with it when it's not in such high dimensions. So for example, if you've heard of Word2Vec, this is just kind of like the example of representation learning in terms of taking words and mapping them into a lower dimensional space. That kind of preserves some of the relationships between the words. So for example, if we look at man and woman and king and queen in this space, in this case, it's a toy three-dimensional space. We can see that the relationships between those two vectors in three-dimensional space are similar based on the male-female kind of tense of the word. And then looking at verb tense, those have similar representations, and then different types of words that might have different relationships with each other, like country and capital, are related in some way. So basically, this is trying to take that information and still preserve it, but kind of take out that large dimensionality that we originally have, where we're working with thousands and thousands of words, which means working with vectors that are thousands and thousands of dimensions long with only, they're one-hot vectors. We're looking at it where every word is its own one-hot vector. So this is similar to our kind of action space in when we're dealing with data and actions online. And so we can kind of like translate this to a financial example. So in this case, we can kind of think of different types of events. So an event type embedding as having similar relationships with each other. So maybe a withdrawal and a deposit in an ATM is similar to a credit and a debit with your credit card. So we can kind of map maybe the way that these things happen and the relationships between them in our really high dimensional action space to another lower space where these can kind of figure out these relationships between these types of events. We can also do things with sequence models, like taking certain sequences of these actions and also embedding them into a lower dimensional space. So for example, in NLP, you can basically take words in a sentence and average their word vectors, and you get some sort of embedding for your sentence. So it kind of retains that meaning of that sentence. And the same thing kind of here is, okay, maybe we can look at this top person here, and they look more like they are trying to charge off and commit fraud. So they lie in some embeddings, part of our embedding space where there are more fraudulent accounts. And this person right here might look, okay, maybe they look like they're more doing money laundering here. They're getting wires, they're depositing and withdrawing money. And maybe our normal customers lie somewhere else in our embedding space. And so this is kind of a toy example here. Usually we work with more than 2 dimensions, and usually there's no defined axis. So we don't know that this direction necessarily means that they're more fraudulent, but we know that some of these different dimensions in our embedding space do mean different things and can help us to still model this action space that we're going to be looking at. So there are some representation learning advantages when it comes to using it in our industry. The first, and I think one of the most important, is production efficiency. So this kind of helps us to condense a lot of the pre-processing of all this data and feature engineering into kind of this one process that other teams can use downstream. So once we have these online actions embedded into a lower space, other teams can just use those embeddings for their models, and they don't have to do any of that pre-processing. You might think that, so basically, like, if you think of the way that maybe you would normally go about it without this is, oh, okay, let's look at feature engineering these actions. So, okay, how many times did this person land on this page in the last 10 days, in the last 5 days? How many times did they do this action before this action? So it gets to be, you can make infinitely many features that you can think of. And it's kind of tedious to do all that when you can probably just do something that tries to capture all this meaning and put it in a lower dimension that doesn't need as much pre-processing to it. And we can basically take a lot of information from different parts of the company and combine it into this process so that there's kind of just one place to go for all this data, and there, you don't need to take from these different lines of business, these heterogeneous types of data. The other thing is data privacy. So embeddings basically transform that feature space, so it's not interpretable by humans. So you can't really backtrack it to any customer data. This is also partly a downside too, because it reduces the ability to kind of explain these models and give some sort of reasoning as to why they're making the predictions that they are. And finally, we can basically not have to deal with these sparse data sources, which means just basically less, having less need for, using a lot of memory, using a lot of storage for when we're, building these models. We can just deal with these lower dimensional spaces. So when we talk about kind of doing representation learning for users and customers, kind of one of the first thing that comes to mind is recommendation. And so recommendation has been used in the past for like collaborative filtering to try to basically create from combinations of users and items or users and movies to try to extract based on people's ratings or their actions in terms of buying and viewing items, to extract some vectors that have some meaning about the user and what their likes and dislikes are. And so recently, since 2016, 2017, there's been a rise in the use of recurrent models for this purpose. And it's kind of an obvious place to go because they're doing kind of these sequences of actions to try to figure out what the user's interests are. And so, for example, recurrent recommender networks did this with movie recommendations, where they modeled users and movies with recurrent neural networks to predict ratings. And then later, latent cross came along, and this is YouTube's recommendation system at the time. And they basically looked at using features about the last video that you watched and other context about kind of what browser you're on or how much time has passed, and making a prediction over the set of videos. So they're basically doing a video ID softmax. So they're predicting probabilities for what video are you going to watch next, and that will kind of drive some of their recommendation. And so there's been a lot of different recurrent recommendation works over the last couple of years, and these are a few of the ones that we kind of paid attention to. And these go from kind of looking at it from a all with recurrent neural networks using point processes to determine, okay, when is someone going to make their next choice on what item they're going to choose and what item will they choose. Looking at it in terms with time LSTM to try to better incorporate how time passing between these different items that you're buying or movies that you're watching affects your decisions, and other types of models that I'll get into later that have come out of this progression. Oh, I think I skipped. So Jody was the most recent one that kind of made a big leap forward in terms of recurrent recommendation. And so they basically treated this like a network. And so you can kind of think of interactions between people and items as a bipartite graph. And it's a graph that's changing over time. So at every time step, we have a different edge that appears between a user and an item. And so over time, these things are changing. And so basically they want to model it as taking an RNN to model every single interaction. And one of the big things that they did is, in the past, what has happened with recurrent recommendation systems is there usually been some sort of like softmax to predict different probabilities of items. But this can get to be a little bit computationally cumbersome. And so what they basically did is they changed the problem to try to also predict the item embedding. So they keep track of an item embedding and a user embedding, and they're kind of both in the same n-dimensional space here. And they try to predict so it's basically a regression to predict the n-dimensional embedding of the item. And they use any like cosine distance or any kind of distance measure to measure, oh, okay, which item are you closest to in this space? And that's their prediction on what they should recommend. And so this also provides them for a way to kind of project forward in time the user embedding. So they basically have some sort of what they call time attention that takes the user embedding, and based on the amount of time that has passed, they project it forward. They project it in the space. So if 10 minutes has passed, maybe their embedding hasn't really moved that much, but maybe 10 days have passed, they've moved closer to another type of item. And so they kind of model it in this way, where these items and users are all moving around in the same space, and they're trying to basically try to predict where they're going to be moving to next. So Jody is designed for this recommendation task, but it can also be viewed as a framework for basically just developing these dynamic embeddings over time. So the next one is called CoSeNN. This is by Spotify, and so Spotify kind of built on Jody's implementation in that they try to look at the sequence of user sessions when they're trying to create their user embedding. So every session is basically just a collection of songs. And in this case, this was kind of the first case where we don't have a recommendation. We don't really have a recommendation of items in this case, because if you think about it, in this case, the songs are really what the item would be, because there's a certain set of songs and maybe you want to recommend a set of songs. But in here, they're not modeling single songs and the sequence of the songs that they're listening to. They're modeling different sessions. So they thought of the session as their like entity that the user is interacting with. So, you know, maybe today I'll listen to a couple songs from one playlist, and then later I'll listen to a couple songs from another playlist, and they'll see these as two interactions with their item. So since sessions there can be infinitely many sessions, because you can take, you know, I can listen to one song and I have, you know, millions of choices for what song I can listen to. I can listen to two songs, and then your number of choices kind of blows up exponentially. So what they did was they first took the songs and embedded them just like that you embed Word. So they use Word2Vec to basically take sessions and embed them into their own space, so their song space, and they averaged all the songs in that session, and that's their session embedding. So they basically have this session embedding that they're looking at, and the model is basically trying to maximize how close the user embedding is to the next session. So they want to, just like Jody was trying to predict the next item embedding, they're trying to predict their next session embedding. And in this case, the session embeddings are just kind of fixed based on the songs, because the songs are kind of just static. So they learn those song embeddings first and then use those downstream embeddings to feed as their kind of item. So what we want to do with some of this research is to not only use these representations for recommendations, but also to inform other models about what users are doing online. And this can be potentially helpful in areas such as customer servicing and fraud detection. And since we want to, it's similar to Spotify in that we don't really have items to recommend. We have a lot of these different actions that are occurring. And so we're going to kind of build off of what CoSeNN did. And the other question, you know, we had was a lot. There have been a lot of different types of approaches to try to model this context differently. So how does time really factor into what we're doing, how we're making our predictions? And also, like, what does the other context, how is the other context incorporated? So how do you incorporate, like, what browser they're on, what time of day it is, other types of information that they would use for in latent cross for YouTube video prediction. And so they would basically kind of take that context, and if we go back to the image here, so they would take that context and do element-wise multiplication before and after applying recurrent units to it. So there are different ways that people have approached this. So we have a lot of context, and we wanted to see if ours would behave in the same way. So as I stated before, we have these online activities here in the form of these events. And then on the right here, we have all of our financial context. So these are features that are available as of the time of the session when someone logs in. So we can see, okay, what is your credit card utilization? What payments have you made? Have you had any fraud alerts in the past like 36 hours? Have there been any emails that have been sent to you? So using a lot of this information, this can provide us context as to what they're doing online. So this is a much larger set of features than were used in these other models before, and they're also in a different modality. Some of the other ones were, okay, what's the context in terms of what you're posting on Reddit? So some of the problems we're trying to figure out, okay, when is what page are we going to recommend for posting on Reddit? And so their context was text. But in our case, our context is a little different and is kind of in the traditional sense of kind of tabular data, where you have these features on different, you could have categorical features, you can have features on different scales. So trying to see how it reacts to having that kind of data. So what we did here was, again, treat our clickstream event tokens like word tokens and embed them in a certain space. So our first step here is not looking at the customer. We want to look at the single session because we're going to be treating this as like our item in our recommendation problem. And so to get our single embedding for a session, what we do is we could use Word2Vec, but in this case, we chose to use sequence-to-sequence autoencoders. So basically feeding in these page views, tokenizing them into these single actions. Each of those receives an embedding, pass that through an LSTM, and you get your latent hidden state and you try to reconstruct it from that hidden state. So from that, we're basically able to say, okay, if we can take in all this information and compress it into this d-dimensional vector and reconstruct it again, then we understand the data well. And so this is basically kind of a way of doing self-supervised or unsupervised learning, however you want to call it. So once we have these sessions, the session embedding, we also have the context at that time as well. And so we want to combine that with, okay, they're logging in at certain times. What are they doing in those sessions, and what does it mean, and what context goes along with that? And we want to combine that to be able to create some customer embedding at a certain time, and be able to use that so that we can have a good understanding about what they've done online in the past, and having that optimally capture some of that activity. So this isn't the full image, but we have the full image on our paper, but I can kind of take you through some of this. So to embed all of this into our customer embeddings, we want to, first we have our sequence of digital sessions. We have different modalities of time. So looking at this as time of the day of the week, and all these other things that might affect why people are logging in, or patterns in which people log in, and different transformations of that. So different like Fourier transforms of that. And also taking some of the offline context features, which is what are our financial features up to this point in time. So as of the time of the digital session, what is their account balance, what other types of financial activity has been going on in the recent past. And what we do is we model all these in parallel in the same with a LSTM to model basically, okay, what's going on over time with these different sessions. And we're going to basically take and fuse those together with an MLP and pass that. And now we have and we basically project that into a smaller space with another dense layer, and we have our customer embedding. So this customer embedding is basically comprised of, okay, what is our understanding of all of these different sequences of sessions and context. And then what we do is with that customer embedding, we project that again out to train this and do our self-supervised learning. We're projecting this into our next session embedding, which we call S hat. And so what we're trying to do here is, okay, just like Jody, we're trying to predict our next session. So what are we going to do in our next, what is this user going to do in their next session? And the way that we do that, the only understanding of sessions that we have is their embedding. So we're going to basically just do a simple projection to their embedding space and minimize the cosine distance between their actual next session embedding and their predicted session embedding. And so this should move our parameters in a way that makes it so that our customer embedding captures some information about what the next predicted session should be. So we have it tells us we have a good understanding about how good we're representing their online activity. So we basically take this approach and compare it to other types of baselines and and some of the other papers that I had shown before. So the first, we took the previous session embedding and said, okay, let's see if it's better than just using the previous session embedding to predict the next session embedding. So that basically gets you this 0.221 cosine distance, and then it improves from there. We do slightly more advanced things. So we say, okay, let's take the average of the last session embeddings and see what that does, and then see how well that predicts the next session embedding. Take an exponential moving average, and then we use some of these different methods. And so ours slightly outperforms it. And we think it's just because we're using these parallel sequential models to try to understand our richer context a little bit better before combining that with our session embeddings. So we also wanted to try this on some other kind of downstream applications of this, because this kind of just shows, okay, how well are we doing in this self-supervised setting where we're just trying to predict the next session embedding. But we basically wanted to use this to do a couple of things. One is predict session intent. So the next session, when they log in, we want to be able to anticipate their needs and basically provide some good customer experience, or prompt them with a message from the chatbot as to what they might want to do. So we have some of the intents where we label what the customer wanted to do when they logged in based on what they actually did. So these are just labeled sessions. And there are about 16 or 17 different intents. And you can have multiple intents in a session. So you can be logging in to check your statement, make a transfer, and pay a balance or something like that. So you can have multiple of these. So we treated it as a multi-label classification problem. So what we do here is we're trying to evaluate the efficacy of our model. So we're trying to compare this against other baselines that we would have used before. So what was being used before was just this financial context. So this financial context was that financial information about your account, and that gets some. I forgot to mention this. We also basically average the area under the curve for all these multi-label classification problems to evaluate these. So using this AUC, we see that context only provides a pretty low prediction power. We also tried using just an LSTM over all of the information and not feeding it in separately to create the customer embedding. So if you remember this page, so if we just fed all of this information into one LSTM by itself, and then our digital customer embedding. So this was basically done by, okay, we take our customer embedding, we slap on just a logistic regression basically on that to do that prediction. And we achieve much higher AUC. And then again, what we do here is we use that same approach, but also include the context again. So we basically concatenate our customer embedding and our context and make that prediction again. So this shows that we're not really capturing all of that context with what we're trying to do in our self-supervised learning techniques. So we're not really capturing all the information there. So there's some being left out, because we can, if we're providing that information again, if all that information is contained in our customer embedding, this shouldn't provide any lift. So we saw that there was some lift there. So there's some ways to go in terms of how can we efficiently incorporate that information and have it in the embedding, because ideally we would like to not ever have to use the context and just give the embedding to other teams to use, and it be kind of a good representation of that customer. So next we looked at customer call prediction. So a small percentage of customers call the call centers after each session. And so we want to be able to triage and predict kind of demand of these calls that might happen to manage that call center. So we set up a problem where we had a label if the customer called within 6 hours of a digital session. So they logged in, they logged out, and then within that next 6 hours, did they call in? And so what we compare that against was against the context. We get, again, a pretty low performance. Then we used SI, which is our session embedding for that one session. So with the understanding of that just one session, can we predict if the user is going to call in? And then we also did, okay, let's take our session and our customer embedding and how much information does that give us about this problem? So it was a small lift above that, but the session kind of captures a lot of that information. And lastly, we looked at account takeover fraud. So this problem is basically, has someone kind of infiltrated someone's account and changed the password and basically just taken over their account. So the way that this model worked before is it's kind of a rule-based model that they've been using, trying to move it over to some sort of random forest model, which is called PRE. And they usually, in a lot of our lines of business and certain applications, we have investigators that have to look into these things. So we want to minimize the amount of work that we need to do. So we have what's called basically like a challenge rate. So out of all the different accounts that we have, out of the millions of accounts, how many should we be going through a day? Like how much can we feasibly go through a day? So if we can only go through 1% of the accounts that get flagged every day, so then we can put the challenge rate at 1%. So what we're saying there is, out of the top ranked in terms of probability of account takeover, in the top 1% of those predictions, how much of the fraud did we recall? So the rule-based method, at some fixed challenge rate, we're able to capture 26% of all account takeover fraud. With the random forest model, we're able to do that with 38%. We're able to basically recall 38% of the fraud, and adding on this customer embedding to this model improves that actually a decent amount, and we're almost able to recall half of account takeover fraud. And so if you're familiar at all with some of these explanation methods, right, we kind of tried to evaluate whether the customer embedding, any of the dimensions of the customer embedding were kind of involved in making a lot of these predictions. And you can see that some of these are features that they had in their original model, which is a non-DCE, non-dynamic customer embedding feature. And the other ones are customer embedding features there. So they provide some, they're some of the most important features that make those predictions. So we have a lot of other things that we want to do here. I think this is a good step forward in terms of incorporating representation learning, but there are a lot of other digital sources, such as data for customers when they aren't logged in. So if you're just like on the website and we're just looking at it based on cookies that are on your browser, or looking at better session encoding. So a lot of progress has been made in terms of embedding in the language space and using transformers. So, we've been looking into how to apply that to session embeddings and how will that improve our understanding of what goes on in a session. Looking at how we can better incorporate this context and fuse it with our understanding of this session, and how can we take in these different modes of data. And this is a kind of a big space in terms of tabular self-supervised learning and tabular neural modeling in general, because most tabular data is modeled using gradient boosted trees now. And so how can we incorporate some of those methods that are coming out to make this better? And then kind of a good place to get would be joint learning with actually the transaction sequences. So we're working with these actions in the digital space, and we're just using kind of summarized features from the financial space. But the ideal place that we want to be is, let's have all of these actions be in the same set of actions. So we can have a deposit action, a credit action, purchase, payment action, all these different actions, and model them together instead of summarizing some as context and trying to incorporate it later in the process. And so that's it for my presentation. Yeah, so I'm open for any questions that you all have.
Thank you so much. Yeah, does anybody have any questions that they'd like to drop into the chat box or ask at this point? Someone did ask if this would be available recording. Yes, it will be on our YouTube channel. DSI has a YouTube channel. Okay, fine. Sent us a question as well. Do you try out transformers instead of word to vec?
Yeah, that's the next thing kind of on our roadmap that we're trying to do, is to look at how transformers can kind of help us improve our understanding of those sessions and sequences of actions in those sessions.
How do analysts, how do analysts look at the results of the system?
So that probably varies across different types of fraud, and there are different ways that we probably deal with certain types of fraud.
Sure. Leo actually sent a clarifier. Example, how would a fraud analyst interpret results?
What if systems look fraud analyst interpret the result? So maybe you're saying from the actual prediction of our model. So these were experiments that were run, so these aren't in production yet. So I can't answer that as to this model, but Again, they show up in different ways, and that's also one of the things that we look at is trying to kind of contextualize some of these results and provide people with as much information as possible as to why the predictions made, other information about that person. People that work in anti-money laundering provide also like visualizations of connections over a graph and stuff like that. So we try to provide a lot of different tools to see predictions and make decisions based off of them.
Got it. It's understood. So speaking of context, one of our participants, Kenny, asked, did the pandemic possibly cause a change in customer behavior? If so, did you have to tweak any of your work because of that?
Yeah, that's actually a good point. All this work was after the pandemic, but I think in our list of things to do is definitely using these to kind of detect shifts in the overall like global population of activity, or also trying to take these embeddings and create like customer segments in terms of how people are acting and seeing if those are moving over time. So that's definitely a good point and something that we want to look at.
So how is model drift managed, e.g. e.g. avoiding false positives over time?
Yeah, so we're currently putting this into production now. So I don't have the full answer for that, but we're looking into also ways to detect drift, and we've discussed ways to how to best do that in embedding space, because it might be a little bit different or a little bit harder than doing that in actual feature space, and kind of less interpretable as to what's happening there. So I think that's something that we definitely are going to focus on before that it gets fully productionalized and disseminated. But I imagine it would be a lot of trying to look at differences in distributions of our embeddings over time.
Awesome, thank you so much. And Leo, the person who asked the question, also says thank you. Thank you so much. If we have any follow-up questions, please feel free to pop them in the chat. I'm just going to ask Sam some questions that we have for our iCubed speakers that usually are very big interest to our student participants. So Sam, how did you get to being a data scientist and a machine learning researcher here at Capital One?
Yeah, so I guess I'd say I always really liked math, so I knew that was kind of my path here. I started out as a math major, and I went to Oberlin College in Ohio, and I was part of the combined program with Columbia. So I got very interested in operations research and optimization, and so that kind of led me there. And in addition, I had also gotten very interested in baseball and statistics, so that was another passion of mine that kind of drove me to the math route and the analyzing data route. And so I after I got out of Columbia, after doing the operations research undergrad, I worked as at Booz Allen as a consultant in the public sector. So I was doing a lot of things that I really wanted to use a lot of the things that I did in school. So I really wanted to apply everything that I had learned and use all those techniques. So I was doing a lot of things around doing projections of budget, like simulations and resource optimization. And so applying a lot of that, and I got into kind of at the end of undergrad in Columbia and also at my job, using different types of machine learning techniques, and got it more interested in that. And so decided to go back to Columbia and do a master's in CS. And so that was really great in that, it definitely provided me, a better background in a lot of this, and a lot of research. So, it helped me be able to kind of interpret papers better, read through literature, kind of implement these things, understand the theory behind these. So I've always been, very interested in knowing a lot, knowing a little about a lot. So I feel like I've kind of going through like math operations research and CS. I don't know if I'm an expert in one thing, but I've experienced a breadth of different topics, and they're all kind of interrelated. You kind of figure out as you go along, and that like operations research can almost be thought of as computer science, and they're kind of interchangeable in a lot of ways. And during that time, I actually worked at Major League Baseball, so that gave me a chance to do apply a lot of that stuff there, and so that was really cool. And coming out of my master's program, I wanted to do kind of a job that was at the intersection between doing some of that research type work, but not quite in academia, but also working with real data and actually, doing applications of those techniques. So this kind of landed me here, and it's kind of like the perfect combination of both. So
that's awesome. Thank you so much. And so happy to have an alumnus back. We're down the hall from us in computer science. Yep. And IOR above us too.
Yeah.
Building. Speaking of applications of data, a question that our students are very curious about are what is the type of data that you work with on frequently, if not a daily basis?
I would say not image data. Mm-hmm. That'd be the one thing that I don't work with on a regular basis. I would say anything from, I guess, depending on how you look at our data, I work with a lot of tabular data because we do deal with a lot of information in terms of a tabular format, but you can also look at our data, as you've probably seen from this presentation, in sequential format. So working with kind of sequential data and tabular data a lot. And we also do a lot of experiments, sometimes with synthetic data. So we're making our own, or when we're working with universities and we can't share data, we need to think about ways to kind of create data that looks like ours. Yeah, that's basically kind of what I deal with on a daily basis.
Very cool. Thank you. So since you know the landscape of Columbia students so well, and this is something I ask of our speakers, so don't think I'm singling you out, but what do you think our master students, our DSMS or other Columbia students, what do you think they should make sure to have under their belt before they go out from graduate studies into the industry world after their master's program? Like what kind of, even if it's a certain type of skill or class they should take?
Yeah. Yeah, I don't know about a specific class. Right. But yeah, but I definitely think that doing, and I think it also depends on like what kind of role you want. But I guess I think at least in terms of my experience, like doing a lot of your own projects or class projects, even like taking classes that do these projects helps you with one actually kind of applying the things that you're learning, and I think the best way to learn is by actually doing it, instead of like kind of learning about it, because you learn about it but you don't really keep it in your brain until you actually kind of use it. So I think it's something that I think is valuable, is even if you're don't have classes with their own projects, maybe doing things on your own, like if you want to work in somewhere that does if you're interested in NLP, like implement one of the big NLP models that are out there, and try to build it yourself. And that's kind of where you get some of the experience, and like, okay, how do I implement these things? How do I understand them? And translate that, and that'll help you when you're kind of at a job and you're like, okay, how do I problem solve through it? You've already kind of done that on your own, and so you can kind of work through that. And so that's something that you sometimes don't get in class, that I found valuable.
Awesome. Yes, thank you. Yes, someone said that's such good advice, and it definitely is. And specifically in our master's program in Data Science Institute, we have a capstone project at the very last final semester. And so a Capital One has done some with us in the past, and we look forward to doing future ones with you as well. But yeah, hands-on learning, getting that actual applications experience.
Yeah.
And as my last question, as we're running out of time, would you mind sharing with us what like a typical day for you would be in your role?
Yeah. So I work on different problems ranging from sequence models to explainability to graph ML. So I think my day probably consists of maybe a little bit of reading. So maybe there are new papers that are out and I need to catch up on some reading. We also, in our group, we do lit reviews every week or two. So we like go through a paper. So maybe one is, reading about that. Maybe we have a project right now about trying to evaluate explanations. So maybe I'm trying to code up an experiment to like answer a question that we have about like, why is this method better than this method? Working in a Jupyter notebook, kind of a lot of the things that you might do in school as well, and just kind of running some of those things to try to answer some of these questions, which bring up more questions, which then, we come up with more experiments to work on, and maybe that leads to a paper that we come together and write and submit for publication. And then maybe some other times in the day, I'm looking through our large amounts. For like graph data, we work with very large amounts of data with probably like billions of edges. So maybe trying to figure out a new technology. Like I didn't know Spark very well, so I didn't really like go take a class on it. I just kind of like started working with the data, and that's kind of ties into like learning on the job kind of thing. So I basically kind of just learned that by going through the data and trying to come up with ways to how are we gonna model this in a certain way. Reading papers that align to that, and then maybe I'm now trying to implement this paper. Or take code that's currently available and apply it to the data, because it has to be changed in some way, and then run some experiments on that. And maybe that gets more towards the applied side. And so we're working with another team to see, maybe we can productionalize this. So there are different aspects to it, and it's a good mix of kind of reading, applying, and kind of the academia and industry mix there. So.
Awesome. Thank you so much, Sam. And thank you so much for joining us today for today's talk and our iCubed. Thank you for our participants for joining us for today's talk. And we look forward to having you back and having you participate with Institute.
Yep. Yeah, thank you. And
you.
feel free to reach out on LinkedIn if you have any other questions or want to talk about Capital One opportunities. Yeah, feel free to reach out.
Wonderful. Thank you so much.
Well, thanks.
Bye-bye.
Have a good one.